Hello, friends. You know what time it is. It's dynamics time. My dog's getting a little antsy because it's like lightning and thunder outside. Well, it was a little while ago. So he's getting a little nervous. So I thought I'd bring him on stream to say hello. Hello! It's Rocky. He's the best. Okay, enough of that. It's dynamics time. Hope you liked my meme today, Groundhog's Day. I don't even know if many of you have seen that movie. It's quarantine day again. Announcements. Your homework number 5 is due tomorrow. That is on conservation momentum and impact. So first 3 problems you should be able to do already. The last problem is on impact, and that's what we're going to cover today. We'll do an example problem. Your simulation number 2, which is on work and energy methods, is going to be due next Tuesday. So take a look at that, take a crack at that. You already have all the tools in your tool bag to do that. So you should be able to kind of execute that at this point. All right. Is there any ado? There's no ado in the chat. All right. If there is no ado, then let us ado some dynamics. Just a reminder, we were working on impact, and yesterday I'd kind of done like a review of stuff that you should have learned in 2002, and that is generally like oblique impact. All right, so let's review impact. And specifically, we were looking at particle impact to kind of motivate our discussion. And remember, the general setup was something like, we had some initial conditions where like puck A was hitting puck B. Okay, here's puck A, here's puck B, and they're going to strike each other. Let's say this guy is moving here with MB A1, and this guy's moving here with something like MVB1. They're going to strike each other. We had some definitions for some vocabulary that we're going to use to describe this impact, namely that we have this normal to the point of impact here, which we call the line of impact, or LOI for short. And then 90 degrees from that, we had this other direction, which is the tangential direction, sometimes given little t. And we define some unit vectors along that general direction. So if the point of impact is right there at that heavy dot, then we have a unit vector along the normal direction, which is E hat n, and we have a unit vector along the tangential direction here, which is E hat t. All right, so this is some general definitions of what's happening when these two objects are about to collide. Then we have some impulses which occur. If we're looking at the system as a whole, so puck A and puck B, then we're not going to see any external forces, because whatever forces are transferred between the two pucks at this point of impact is going to be internal to the system. So you see nothing. Nothing. And then your final momentum is they've struck each other, and now they're moving away. They had a brief stint, a brief relationship, short and fleeting, where now they've rebounded off each other and have some new momentum terms. So here this is something like MVA2. And after this guy strikes, maybe this guy is moving now this direction with something like MVB2 after it's kind of struck that particular guy. All right, so we talked about this general situation, and this looks a lot like what is kind of a impulse momentum diagram. And we used this impulse momentum diagram to look at conservation of momentum in the E hat t and the E hat n directions. When we did that, we came up with 4 different equations. All right, so by conservation of linear momentum, we saw mathematically we had these 4 equations which end up being important for us. That the velocity of the puck A, state number 1, specifically in the tangential direction, is conserved. So whatever it is coming in, tangential direction, it's the same coming out. This was for us kind of like equation number 1. Same thing with the velocity of puck B, state number 1, tangential direction. Whatever it is in the tangential direction going in has to be the same in the tangential direction going out. This here was like equation number 2. This comes from conservation of momentum of each individual particle in the tangential direction. Since the impulses on these particles are only in the normal direction, the tangential momentum must be conserved. Okay. So this is specifically conservation of momentum in E hat t. Right? For E hat n, we looked at the system as a whole and said that the system as a whole in the normal direction must conserve momentum. And that led us to the following equation. That is the mass of puck A times the velocity of puck A, state number 1, plus the mass of puck B times the velocity of puck B, state number 1, equals the mass of puck A plus the velocity of puck A in state 2, plus the mass of puck B times the velocity of puck B, state number 2. All of this in the normal direction. All right, so specifically in the normal direction. That's a funky looking M. Dang, looks like a drunken M. Okay, that's a little better. All right, so this was like equation 3 that is used for us. And then the fourth comes from conservation of energy. We have the coefficient of restitution equation. And coefficient of restitution, we use the variable little e. And we write for coefficient of restitution equation that the velocity of point B, state number 2, specifically in the normal direction, minus the velocity of puck A, state number 2, normal direction, is going to be equal to this coefficient of restitution times the velocity of A, state number 1, in the normal direction, minus the velocity of B, state number 1, normal direction. All right, and this for us is equation number 4. This comes from conservation of energy. And we know that this coefficient of restitution E ranges in value from 0 to 1. Okay, and these 4 equations were specifically for particle motion with oblique central impact. All right. And we made some definitions for what it means to be an oblique impact. That is that the velocity is not on the line of impact. And central, meaning that the masses are on the line of impact. Okay, so when we talk about particle collisions, which is kind of what we just drew, the masses are always on the line of impact because the mass is this tiny infinitesimal piece. So the mass must always be at the line of impact because it's the center of gravity. There's nowhere else for the mass to possibly be. All right. Oblique impact is, again, the velocity is not necessarily in the line of action, which we kind of drew up in this figure here. We see that this particular velocity is not on the line of action. So this is an oblique impact. Right. Now, that's all good and great. What do we do when we have to go to rigid bodies? Well, again, rigid bodies, you're not going to always have this central impact. You're going to possibly have eccentric impact. And I'd say most of the time you have eccentric impact. So we have to deal with that. All right. Can you deal with that? Okay. Anybody know the movie? If you know the movie, I'll be very impressed. Can you deal with that? Okay. 10 million bonus points of nothingness to whoever knows that movie quote. All right. Can you deal with that? All right. we have to deal with moving from particle interactions to rigid body interactions. So now let's investigate rigid body collisions with eccentric impact. Looks like somebody has a guess. Can you deal with that? Meet the Parents, David. Rawr, good job. Gaylord Fokker in that movie. Can you deal with that? Such a good movie. All right, so we're going to investigate rigid body collisions with eccentric impact. So what we should have in mind is some rigid bodies with some just random generic shape. All right, so let's say we have like some peanut-shaped rigid body. Maybe it looks like that, and it's going to collide with some other peanut-shaped rigid body, you know, that looks, I don't know, something like this. All right, so here's rigid body A. Here's rigid body B. This guy has a center of gravity. It's probably not going to be there. The center of gravity might be something more along the lines of there. And here's the center of gravity of point B. So let's call this GA, and we'll call this GB. And they're going to collide down here at some point that we'll note down here, and we'll call this, let's say, point D. All right, they're colliding there. So two bodies, A and B, colliding at D with eccentric impact. Terrible. All right, so it's eccentric because the centers of masses of those individual objects are not along the line of impact. So if these guys are going to collide together and hit each other, remember the line of impact is like normal to that collision site. So the line of impact here is something like this. Right? Notice that the center of gravity of each of those objects is not necessarily on that line of impact. So we got issues. All right. And just, I'm talking dynamic issues here. We all have our own issues. Okay, come on. I'm going crazy here, so obviously I have issues. All right, so the collision has got this line of impact, and we see that neither of the centers of gravity are along that line of impact. So when they strike each other, you're going to impart motion in this angular sense because there's going to be resulting velocities at the line of impact after the collision, and they're not necessarily at the center of gravity. So you're going to impart rotation to each one of these objects, and that kind of complicates the matter. All right, so how do we deal? How do we deal with that? Can you deal with that? All right. Well, we deal with that by applying the four equations that we previously wrote for oblique particle impact to the particles that make up the point of collision. So the point here is that the equations that we've already derived hold, and we can determine what the velocities are right where those two things hit each other. Then we can use relative velocity equations to propagate the information about the two particles that are hitting each other at that one point of the rigid body to various other points on the rigid body. So we spent a lot of time talking about like rigid bodies and their collections of particles. You got to think if two rigid bodies are hitting each other, that it's like one particle on one rigid body hitting another particle on that rigid body. So we can do the particle dynamics analysis with those two particles that are hitting each other right at that particular point, determine what the velocities are of those various particles on that piece, and propagate that information to the rest of the rigid body. That's all there is to it. So the way we deal with eccentric information is, so here, we do particle analysis for both objects at point D, and then use kinematics to determine other velocities. on the body, including potential angular velocities. All right, so velocities here, I'm including both linear and angular components. All right, can you deal with that? So enough jibber jabber, enough yakety yak. Let's do it. Let's do an example problem. Right? Yakety yak, don't talk back. So let's look at an example problem. This example problem is very similar to problem number 4 that you have on your homework, right? Except here we're sort of vertical instead of horizontal, and we've got a different location for the pin. But the general idea is the same. A 2 kilogram sphere moves to the right at 5 meters per second, and it strikes the bottom end of this rod, which weighs 8 kilograms, sorry, has a mass of 8 kilograms, and the coefficient of restitution between the sphere and the rod is 0.8. We want to determine the angular velocity of the rod and the velocity of the sphere immediately after this impact has occurred. Okay, so this is an eccentric impact because the center of gravity of the sphere and the center of gravity of the rod are not both along the line of impact. So there's going to be resulting angular velocities. We have to figure out what that is, and resulting post velocity of the sphere, which is going to be different than the velocity of the rod where the sphere strikes it. So let's look at this example. Go ahead and copy it down. And I will do the same. Let me ask you a question, Jack. Can you deal with that? All right, let's get you over. All right, mass of the sphere, 2 kilograms. Bam. Mass of the rod, we're given 8 kilograms. Bam. Coefficient of restitution between the two things, 0.8, given. Bam. Velocity of the sphere coming in, 5 meters per second I hat. All right, we're going to assume traditional XY coordinates in this problem. We're asked to find the angular velocity of the rod and the velocity of the sphere in state number 2 after impact. All right, so I label this as VS2 and omega R. And I'm kind of labeling them as magnitudes here. We'll kind of see how the direction shakes out as we go through. Okay. So this is a conservation of momentum problem. And with conservation of momentum problems, we're going to attack them by doing conservation of momentum of our particular problem with our sort of momentum diagrams. So we will do an initial momentum. We're going to have some impact or some impulses. And then we have a final condition. So initially, here is our rod. Up here we have what is point A, and down here we have what is point B. And it looks a little bit weird in this figure. It looks like the velocity is kind of like hitting some random point up here, but we're supposed to assume that this velocity is impingent on the bottom of the rod here at point B. Okay, I don't think they did a very good job with this figure. But if that's the case, we have this linear momentum coming here, which is the mass of the sphere times the velocity of the sphere in state number 1. And initially we're told that the rod is at rest. So the only thing kind of coming in here is the mass of the sphere times the velocity of the sphere in state number 1. Maybe it's worth drawing both objects just to make sure we're crystal clear about what's going on here. So here's the sphere coming in and it's striking B. And this is coming in with mass of the sphere, velocity of the sphere, state number 1. Just to be crystal clear that there's two objects that are hitting each other, and object number 1, the sphere, is the one that's moving. The impulses here Here's again this kind of point A. Actually, I'll do this. Here's point A, and here's the sphere, which is striking the rod. The sphere is striking the rod. Yes, there are going to be forces that are transferred between the sphere and the rod. But since we're considering this as a system, the forces that are transferred between the sphere and the rod are going to be contained within the system. So these are not external forces because they're contained within the two objects that we have. So the only impulses that we have in this particular problem are the impulses that occur from the pin at A. So here's the integral of the force at A in the y direction over time. And here's the impulse associated with the force at A in the x direction over time. All right, so get your facts straight. Final momentum. Here's point A. I'm going to draw in here now the center of gravity, which is point G for the rod here. And also we have our sphere that's still kind of hanging out here now at the bottom, but let's say that it's right about to or has just released from the rod. All right. So in state number 2 now, obviously the sphere hitting the rod is going to like impart some motion now to the rod. So the rod is just about to begin moving. And so that motion of the rod is going to excite some linear momentum at the center of gravity and also some angular velocity at the center of gravity. So we have some components here because this rod is now beginning to move of something like the mass of the rod, the velocity of the rod in state number 2. And let's be specific here. This is the velocity of the rod state number 2. And this is specifically at the center of gravity, say G. All right. We'll also have some angular velocity that is occurring. So let's just draw it in the general positive direction. Here we have I, G, omega. And this is something that we're interested in finding, this omega value. The angular velocity of the rod after the sphere has struck in the rod. The sphere will also have some residual velocity, yet we don't necessarily know if the sphere is going to hit this rod and bounce back, or if it's going to hit the rod and maybe still keep going after it kind of like swings the rod up. We don't really necessarily know how the sphere is going to move. But the way that we handle this is we just draw this velocity in state number 2 with a general positive sense, and we'll let the math take us there. Let the math set you free. Rawr. So here's the mass of the sphere and the velocity of the sphere in state number 2. Okie diddly dokio. Let's dance. So the way we're going to attack this problem is to say that conservation of momentum is conserved both linearly and angularly. You could do a conservation of linear momentum in y and figure out that there's not really going to be anything happening here. Okay, you could do a conservation of linear momentum in x and you're not going to learn a lot of information. The only thing we really need to have to worry about here in this problem is the conservation of angular momentum about A. So let's look at that. Remember our general equation. Always like to write the general equation. The angular momentum about A, position number 1, plus the impulsive moments integrated over time is equal to the angular momentum about point A, state number 2. All right. Remember, that's our general equation. It's where we always start. Vector form, yay mathematics. So let's check out what's going on with the angular momentum about point A in state number 1. All right, well, here is point A in state number 1, and we're going to have some angular momentum component about point A that comes up from this linear momentum of the sphere. So we need something like, why does it keep doing that? Damn. Here we've got a position vector that locates B from A. So here is the position vector which locates B from A. So that position vector crossed with the linear momentum vector MSVS1 is going to give us this angular momentum about point A. We can generally see that that cross product is going to be positive, but let's kind of just write it down and make our way through that calculation in just a second. So here we're going to have something like the position vector, which locates B from A, crossed with the linear momentum of the sphere, which is ms vs1. That's the only angular momentum component we have to worry about in our initial state. All right. Our impulses now. We have to worry about the moment impulses about point A. And since both of these linear impulses travel through point A, there is no moment arm, so we have no moment impulses about point A. So here, plus a big old 0. I like when I get to write 0 on the paper because that's easy. So easy a caveman could do it. All right. I can add 0 to something. It's nice. All right. Now my angular momentum in state number 2. I've got a linear component here with position vector locating that guy here. So that's going to pop up. This is the position vector, which locates G from A, crossed with the mass of the rod times the velocity of the rod in state number 2. This is specifically at the center of gravity, but hopefully we all kind of understand that. I'm going to add to that the component that comes from the rod now beginning to spin, this IG omega. Instagram omega. Plus the last bit, which is here, the mass of the sphere times the velocity of the sphere. This has some linear momentum. And again, it's located down here at what is point B. Remember, this is B down here. So we have a position vector which locates B from A crossed with this linear momentum component. It's going to be a general positive sense. So here is just the position vector which locates B from A crossed with the mass of the sphere times the velocity of the sphere, state number 2. How are we doing? Any questions? Can you deal with that? All right. So let's put some numbers to all these guys now. We generally know that the rod is 1.2 meters long. So if we kind of come back up here and look, the rod is 1.2 meters long. So the position vector which locates B from A is going to be something like 1.2 meters. And then we know that the half length is 0.6 meters. So the position vector which locates G from A is going to be 0.6. So if we put some numbers in here and use our right-hand rule for the cross products, we can sort of simplify this guy. Position vector which locates B from A, we know that to be 1.2 meters. Multiplied by the mass of the sphere, we're given as 2 kilograms, multiplied by the initial velocity of the sphere, given in the problem, 5 meters per second. All right, so that is my left-hand side of the equation, my initial momentum components. This is going to create for us some final angular momentum, which has contributions from all of these things, as you see. So the position vector which locates G from A, this is going to be 0.6 meters. It's the half length from G to A, multiplied by the mass of the rod, 8 kilograms, times the velocity of the rod in state number 2. We can use a kinematic relationship here between the velocity of the rod at the center of gravity in state number 2 and the angular velocity. It's 0.6 times omega. So remember, I have fixed axis rotation about A. So the velocity at the center of gravity of G equals 0.6 times omega. All right, that's the substitution I have just made. I'm going to add to this Instagram omega. Mass moment of inertia for a slender rod is 1/12 ml squared. The mass of the rod, 8 kilograms, times the length of the rod, 1.2 meters to the squared, multiplied by omega. And finally, this last term here, this is the term for the angular momentum about point A that the sphere provides after it impacts. So here the position vector to B from A, again, is 1.2 meters, multiplied by the mass of the sphere, is 2 kilograms, multiplied by the velocity of the sphere in state number 2. Okay, got to be careful here. The velocity of the sphere in state number 2, since the velocity is rebounding off of this rod, it does not have a kinematic relationship with the rod any longer because it is rebounding off of the rod. It doesn't stick to the rod. So you can't write something like the velocity of the sphere after impact is 1.2 times omega. That ain't right because it's not stuck to the rod anymore. So we have to have some just generic value for the velocity of the sphere in state number 2. So I will write here, this is the magnitude of the velocity of the sphere in state number 2. And I'll make a very specific note here that because the sphere rebounds off of the rod, it doesn't have this kinematic relationship with the rod anymore. It is not the case that the magnitude of the velocity of the sphere in state number 2 is equal to r omega. That is not the case. Or this might be something like 1.2 omega. That is not true. If you write that on your paper, incorrect, because it doesn't stick to the rod. It bounces off. We don't have this sort of perfectly plastic impact anymore. All right. So we simplify above with both omega and magnitude of the velocity of the sphere in state 2 as unknowns. All right, if we do that, we can look back at this equation up here. The unknowns that we have are the angular velocity of the rod after impact, this omega, and the velocity of the sphere after it has impacted the rod. So we can sort of simplify this and write this after doing some algebra. This is going to be something like 12 Newton seconds equal to the contributions here, 2.88 omega. All right, so that's the contribution from this guy, plus the contribution from the next component is going to be 0.96 omega. This is an omega, or W as my students sometimes like to say. All right, so that comes from this portion, which is the angular velocity of the rod itself. And I'm going to add to this last contribution here, which will look something like 2.4 times the magnitude of the velocity of the sphere in state number 2. All right, let's call this equation 1. And we see we have in this equation the angular velocity for the rod, which is something we're after, and the linear of the velocity of the sphere after it hits the rod, which is also something we're after. So we need more information. And that equation that we're going to use is the coefficient of restitution equation. All right. So we've done our conservation of momentum. Now we need to bring in conservation of energy through the coefficient of restitution equation. Let's remind ourselves what that general equation looks like. That general equation is that the velocity of, in this case, I'll sort of denote the rod and the sphere so we can kind of be very clear about this. The velocity of the rod, state number 2, minus the velocity of the sphere in state number 2 equals the coefficient of restitution, E, multiplied by the velocity of the sphere, state number 1, minus velocity of the rod, state number 1. And this specifically applies at B. This is very important. So B is the location on the rod where the sphere hits the rod. So we must do our particle analysis right on the particles where this is occurring. So it's specifically the case that we're looking at the velocity before and after impact of both the rod and the sphere right where they hit each other. So let's define some of these things. The velocity of the rod in state number 2 at point B is related to the angular velocity of the rod, and it will be something like 1.2 times omega. It's this kinematic relationship, because this is going to be the velocity of the rod at point B after the impact has occurred. The velocity of the sphere in state number 2, this is kind of what we're after. This is an unknown, is equal to this value of E we're given in the problem, is 0.8. Here the velocity of sphere in condition number 1, we're given 5 meters per second. And here the velocity of the rod in state number 1 is 0. That's because before the sphere hits the rod rod is at rest. All right. So let's put this all together. Put this here, then we have 1.2 omega minus the magnitude of the velocity of the sphere, state number 2, equals the coefficient of restitution, 0.8, multiplied by this 5 meters per second for the velocity of the sphere, state number 1. All right. Can rearrange this guy and solve for one of the variables. Let's just, I guess, solve for the velocity of the sphere. It's kind of easy. We'll say here that the magnitude of the velocity of the sphere, state number 2, after we simplify, is going to be something like 1.2 omega minus 4. All right, let's call this equation 2. So now we have 2 equations and 2 unknowns. The conservation of momentum equation, which is the angular momentum conserved about point A, gave us these 2 unknowns, omega and bs2. And then our conservation of energy through the coefficient of restitution equation gives us another set relating angular velocity of the piece and the velocity of the sphere after impact. So we'll plug 2 into 1. Do the hokey pokey, turn yourself around. You get something like 12 is equal to 3.84 omega plus 2.4 times the velocity of the sphere, which we know is 1.2 omega minus 4. All right. So this is, again, plugging 2 back into 1, where here is the entry of equation number 2 into equation number 1. All right, well, this is just algebra. We can find here that the angular velocity after working through this is going to be 3.21 radians per second. And we have discovered a positive value for angular velocity in this particular problem. So the positive value here of the angular velocity indicates that when we originally drew our angular momentum vector with this general positive sense, that we did in fact draw it in the right direction. So the math does kind of work out here to tell us that physically the value of omega is going to be positive in the direction we drew, which is what we expect. All right. So 3.21 radians per second, or if you want to write it in vector form, 3.21 k hat radians per second. All right, there's your vector form. We can plug this back into equation 2 to determine that the magnitude of the velocity of the sphere is equal to what is going to be 1.2 times omega, so 1.2 times 3.21 radians per second, minus 4. Or we get here that the magnitude of the sphere in state 2, after working through the algebra, negative 0.148 meters per second. What does this mean? Well, the negative value just indicates to us that however we drew the linear momentum of this object in state number 2 was wrong. It was the wrong direction. So we assumed up here this general positive direction for the linear momentum of the sphere after impact. But we didn't necessarily know that was true, right? So if I've got this plate hanging and I've got some object that's impingent on it, it could either ricochet backwards or it can continue to move forwards, but maybe slowing down just a little bit. Here we drew it as this idea where it potentially continues to move forward, but that was incorrect. In reality, this guy is going to bounce back this way with some very small velocity of negative 0.148 meters per second. So again, just let the math set you free. All right, let the math take you there. So if we wanted to write this formally, we'd say then that the velocity of the sphere in state 2 is negative 0.148 I hat meters per second. So it hits this plate and it rebounds backwards. And that's what she wrote. Can you deal with that? Okay, so that was an example problem. You have a homework problem that's very similar. That's it for today. I'll stick around. People have questions or want to talk about more movie quotes. Rawr.